Okay, so hello. I'd like to present an introduction to TETRA and its use in amateur radio. A few words about us. Marcin, he works Sierra Papa 8 Mike Bravo, he works for the government. He's also the advocate of TETRA in Poland. And his interests are R&D of drones and also digital radio communication systems. And he's also the author of TETRA Logger. And myself, my name is Jacek, my call is Sierra Quebec 5 Bravo Papa Fox. I have been licensed for more than 30 years. And basically I've been doing breaking networking stuff, Unix stuff for also more than a quarter of a century. And I'm interested in all radios, so digital, analog, high frequency, low frequency, like CW, anything, right? And I'm the author of TETRA. So what's on the agenda? We're going to talk about TETRA. We'll see if it can be used in amateur radio. I will talk also about the TETRA project, about TETRA Logger and TETRA GPS, about TETRA, and a bit about TETRA security. So, what is TETRA? This is an abbreviation for terrestrial trunked radio or trans-European trunked radio. It's an SC open standard, almost open. And actually it's just similar to second generation GSM. But of course everything is named differently. And this is often used for critical communications, for government stuff, for commercial. Under the hood it's quadrature phase shift keying, there's 18,000 samples per second. 2 bits, so that's 36 kilobits per second raw data rate. It occupies 25 kilohertz bandwidth, but there are higher bandwidth versions which have more throughput. This is called TETS. However, I haven't ever seen it in the wild. And logically, transmission is divided into 4 slots, and each slot is, after coding, it's around 7.2 kilobits. The operation is what you would expect, like trunk mode operation. So there is a TETRA base station or multiple TETRA base stations, and the radios can roam between these base stations. There is support for handover, stuff like that. And there's also DMO, so that's direct mode operation, and this is just directly radio to radio. Also a radio can work as a repeater, so it can, for example, patch a DMO radio into the TMO network. This is a nice diagram from CERN. So on the right you see the clients. In the gray box you see the switching and management and infrastructure and the TETRA base stations. And the bottom 2 clients are the normal trunk mode operation clients. But there is also a guy on the upper right that is being patched to the trunk mode operation via the radio in the fire truck. So I said it's an open standard. There is a lot of documentation from ETSI. It's really extensively documented. If you have problems sleeping, just read it. However, as in other common radio technologies, the codec is not open. So that's a difference from M17, for example. But at least this codec is, the source is available. So that's a change, right? Because the DMR uses AMBI or some other use IMBI, and this is not is no open reference implementation. And also, if you look at the protocol specifications, it's full of room to insert proprietary extensions. So there is, for example, the specification will say that there is a byte field, and in this byte field, if the field is between 0 and 7F, then these are just some protocols, right, which are specified in the documentation, and if it's, for example, around 80 hex or above, then these are proprietary protocols for vendor extensions. And if you read the specification, it's like on every other page. Also, the cryptography is not documented, or was not documented, and I will talk about it at the end of the talk. So, not open, but like quite open, right? At least much more than the usual DMR, P25 or whatever. And also D-Star, which should be open because it's a ham radio technology, right? So some services on a TETRA network, there is the usual network housekeeping stuff, so the way the terminal can log into a network, the roaming, stuff like that. There are, of course, voice calls, and these can be either group calls or individual calls. And there is also support for having the call in duplex, which means that you hear and say you can speak and listen at the same time, just like on a mobile phone. I said it's similar to GSM, so there is, of course, data transfer, and there is circuit switch data, which is like CSD in GSM, if anybody of you still remembers this service. And there is also packet data, which is like GPRS in GSM. There are also short byte messages. This is the status message. Short messages, which are called SDS, short data service, because it cannot be called the same as in GSM. And like in GSM, this is used like it was used in GSM. This is used, of course, for text, but it can be also used, also binary data can be sent. And this was often used for industrial control or telemetry or similar stuff. And actually, there are a lot of services that will work that use SDS. So this is, for example, location protocols. So the thing that locates the radio, but the thing can also set other stuff, query, whatever. There is industrial control, lots of proprietary stuff. So, can it be used for amateur radio? It is a complicated piece of protocols. It is a bit more open than the DMR, for example. So you have the voice codec. It's something that can be used. Equipment is available second-hand, at least all the equipment. And basically, it's a very nice opportunity to play around with old enterprise radio. You know, a radio that doesn't fit in your pocket, but you need two people to carry it. Yeah, that's enterprise. And also, DMO is easy, right? Because it's just radio to radio, so you have two radios and you can play around it. Unfortunately, the range is not quite good. If I see you, I hear you, but other than that, it's not much further. TMO is not easy. And this is where the TETRA project comes along. So, basically, there is an open source implementation, or the way that the TETRA base stations communicate with the backend infrastructure was reverse engineered. And there's an open source implementation of this. And basically it does 90-something% of what TETRA does. Yesterday we were actually trying to think of what it doesn't do. Probably there is something. So it does all the calls, right? Group, individual, you can have duplex calls. Also this TETRA has provisions also in the protocol to patch the call into another network, into telephony network. So this one can use asterisks as a PBX and do whatever else. Wherever, I mean, forward it wherever asterisk can forward it to. So there is support for these short messages, and also there is support for some specific protocols that work over these short messages. One of these is LIP, which is Location Information Protocol. So that's the protocol to locate radios or send position. And it can be bridged to other technologies, to APRS, for example. There is packet data, and there is support in radios for WAP, just like the old GSM Nokia phones. And with an external WAP gateway, like Canon for example, it can be used to use the WAP system in a phone. It can bridge with other networks. So one network is Brandmeister. So this is the preliminary VMR network. Right now it's not only VMR around the world, and can translate the concepts from one network to another. So there you can do group calls, you can do simplex calls, you can get these text messages across. Also, some of these messages can be put to, for example, an MQTT server, stuff like that. And there's also support to bridge with basically Echolink. So, for example, FM Poland. And you can, this is voice bridging. And also it can use the radio ID database for access control. So if you have a DMR ID, then a radio with this DMR ID can log into the network. A few words about the supported TETRA base stations. There is compact TETRA. There is also Motorola TETRA, which is the stuff that you see, the heavy device that you see, that you can see in the other room, right? Heavy and loud device. 300 watts input power constantly, yeah. Keeps the room warm. And there's also Rockwool equipment. Currently, there are 5 Tetra Pak nodes in Poland. Unfortunately, not here. These are some nice photos. You can see that none of them are small. Regarding the terminal equipment, the handheld radio equipment, these are Motorola radios and also Hytera radios. Now, the problem with terminal equipment is there are basically 3 problems. That's availability of service software. The TETRA standard defines the frequency offset between transmit and receive. And it's hard-coded, so you cannot just say, okay, I want 7 7.6 megahertz, which is the normal repeater offset here. So you either change one of the predefined values to something else, or you just use the predefined values. And one value that is close enough is 8 megahertz. So if you can get a license for 8 megahertz offset between the channels, then it's okay. And Marcin gets to get this license. And there is also a problem to extend these radios to work on the 70 centimeter band, because they are usually until like 400 to or 410 to 430, and then they are, I think, 450 until 470. So you can get these radios you can get some of these radios to tune to the ham radio frequencies. Not all of them. There are some listed here where it's a problem. But the most popular ones are Motorola. Now I'll talk about, you can make a photo of this if you're interested, but on the end of the presentation you will see a GitHub link with this PDF, so you'll have all of it. Okay, I'll talk about TETRA logger. TETRA logger is basically a system device that will connect to a radio, and it will log network parameters. And this is powered by the radio. It's also, it doesn't affect the function of the radio, so you can still use it to communicate. And it can log, it can connect also to a Wi-Fi hotspot, and then it can log this data to an external server. And this is nice for site surveys, stuff like that. The supported radios are Motorola. So it will log basically time, subscriber identity, which is just station ID, location, signal strength, error rates, and then you can plot it on a map to, for example, doing site surveys if you have a mobile terminal. There is also TETRA GPS, and TETRA GPS is just locating parsing lib, so that's location information protocol responses, and being able to draw the current position or historical positions of a station on the map. And this is lib is a hardware, it's a TETRA standard, so most radios will support it. Okay, so now I will talk about TELEF. So in 2010, 15 years ago, Osmocom, which probably most of all or all of you know, released Osmo TETRA. And this was a full implementation of the lower layers of the TETRA protocols, along with some higher level stuff. And the receiver was an RTL, or an SDR receiver, which around the time the RTL receivers started getting popular. And this did decode some signaling information, not a lot, but it was enough to see the cell parameters. And with this information, you could program a radio. And it turned out that magically most of these radios were just let into the network, because there was no encryption and often there was no access control, so people started doing that, I've heard. But a few years later, I made my own fork of this project. So I basically chopped it into a few modules. One was a SDR receiver into the radio companion. Then there was a separate QPSK demodulator, and then the forked core Osmo TETRA software. So I implemented a lot of stuff like signaling, SDS, also the higher level protocols that work over SDS, like location. Also fragmentation, which means that one could receive longer SDS packets, with messages longer than few 10 or 20 bytes. And to simplify things, it would just send all of this information via UDP. And then there was another software, which I called TELife, for the name stands for TETRA Live Monitor, which will receive this UDP and try to packets and try to stitch some meaningful data out of them. And this was nice because it was chopped into little blocks. They were modular. You could replace them, whatever. So this is one example. You can have an SDR receiver. It can be multi-channel also. So in this example, two frequencies. Then you send the data via a pipe or a Unix pipe or UDP or 0NQ. Then you have these demodulators, the Osmo TETRA fork, and then it will send UDP to this TELife program. And also this TELife program can control the receiver via XML or RPC, which is nice because, for example, you can compensate for clock drift in the cheap SDR receivers. So how does it follow voice call? Voice traffic has something which is called a traffic usage marker, just an identifier, and there are messages which will bind this identifier to something else. So, for example, there is a the setup message which will, by the way, D means downlink, so it's the thing that we can receive from the base station. Info about station identifier, call identifier, which is a thing that identifies a whole call, and this traffic usage markers. And there are other messages. So we can use this to try to stitch that this voice traffic belongs to a call, and that some stations are participating in this call. So what TELife will do, it will play one active voice call. It can record all ongoing calls, so multiple calls at once also, and will add the station's ID to the file name. It will also log signaling. It can compress the voice data to OGG. It can, as shown on the diagram, it can handle multiple channels at once. And also it will log the location to a KML file, and you can later open this in Google Earth, just to see the location of stations. And also it will perform network discovery from the signaling information, and it can also control the receiver, so it can do clock compensation, it can tune additional channels if needed, and also it can scan, which is quite useful. So I released this in December 2014, lots of time ago, and this is just the interface, the course's interface. You cannot see much here, but I can show it later. So now I will talk about TETRA security. This is an interesting topic. So early TETRA security was very simple. So we have a very complicated and expensive system, right? Like encryption is an additional expense I don't know what is the cost per network infrastructure, which is like a lot, but I've heard that the cost per radio, because it's not that only the infrastructure, I've heard that the cost per radio is around $100 for the license. Yeah, at least. So, imagine if you have a special force that has 1,000 radios, it makes the cost a tiny bit higher, right? And also to monitor, you would need some special receiver, right? And this special receiver doesn't exist actually. There is one software which is called W-Code. I don't know if at least one person is nodding. Yeah. This is like for software which you cannot normally get. You can get it it's usually for special forces. But of course there are private versions. So no receiver, no problem, right? No need for encryption, problem solved, concept is sound. But actually not, because after I released T-Life, I started to get really weird messages. And this is just an example. So somebody would say, hi, nice work, but please tell me, are you breaking encryption, or how are you breaking encryption, or something like that? And I didn't really know why, right? Why are you, especially that it was mentioned in the documentation that I don't know how the encryption works and how to break it, right? So and this is just an example. So this guy said, okay, because I'm using I'm using TETRA, which is like purchase as a service from some external company, some network provider, and they tell me it is secure, right? But the problem is that I'm able to listen to my own traffic, so there is some discrepancy between what I see and what I pay for. And yeah, this is just only one of tens of messages that I got, and I probably didn't get 100 times more. This is an interesting example. I asked people to send me data that I could use to reverse or try to figure out proprietary protocol, or basically everything that I didn't support. And there is a system called Simple Location System. That's one of the location protocols. And there is a type 80, and 80 is the first, is a proprietary protocol, so there is no documentation. And I try to reverse engineer if there's maybe some geographic coordinates in it or something. And so I got a log on Postman, and actually after reversing this, I put it on the map, and you get lots of these points in one system, in one maybe it's not one place, because this is like, this is Spain, the vicinity of Alicante, so that's like, this blob of points is like probably 200 kilometers across, or 100 or something like that. And this is something that the guy received on one downlink channel in the location where he lived. Right? He didn't tap the whole network, he just received some data and sent it and said, please can you decode it. So it turns out that allegedly this is some police-like force that has cars moving. And I cannot confirm or deny this. But there is, I mean, you can fix all of these problems with crypto. That's easy. Of course, the best crypto is the crypto that you don't know about, right? And it because it's 100% secure, and that's exactly what they put here. So this is non-public proprietary crypto, and it's authored by SAGE, which means Security Algorithms Group of Experts. And actually, nobody knows who these people are. And also it was done in the 1990s, so you have all of the fun export restrictions, Wassermann Agreement, which is actually present to this day, in some shape or form. And basically there are 4 encryption protocols. They are called TEA and a number. This stands for TETRA encryption algorithm. There is a name clash because there is also a tiny encryption algorithm, and it's also called TEA, but this has nothing to do with it. So the first one is like exportable encryption. So basically, if you run, I don't know, a vegetable shop and you need encryption for your radios, then buy that one. Only $100 per radio or more. And the custodian of the algorithm is ETSI. And there's also TA2, and that's for government services in the Schengen area. And the custodian for this is the Dutch police. And also there is TA3, which is for governments but not in Schengen. And basically, if they are friendly enough, then okay, you can use it. And the custodian is also ETSI. And there's TA4, and TA4 is like, okay, if you don't really trust the vegetable shop encryption, then this one is much better. Now at least you can use it if you don't trust the previous one. And there is also a TAA1, which is for key management, distribution, stuff like that. And recently they released TAA2 and TEA5 to TEA7, which are like the newer versions of TEA1 to TEA3. And this time they are with public specifications, and I will briefly talk about why. So if you read the ETSI documents, they say that, okay, you can get you can sign an NDA and some other restricting license, and then you can implement TA1, 3, and 2 to get TA2. Sorry, 1, 3, and 4 to get TA2. You need to negotiate with the Dutch police. But you have to implement it in such a way that it's very, very hard to reverse engineer it from a radio. And actually, we've seen this before, right? Because we had GSM. And GSM had non-public encryption. It was a secret. This secret was stored under thousands or millions of mobile phones, but it was locked in some way. So this algorithm was created in '89. There was partial implementations in '94, and in '99 then you had a very nice leaked full re-implementation. And once the cryptographers started looking at it, it turned out that actually it can be broken with like modest hardware within like 1.5 weeks. And when they started to look more, then actually it could be broken with modest hardware in a few days. And they started looking into it up to a point where right now we have much better hardware. And we can try to break it within seconds with rainbow tables. So that's a cheat, but it's almost lethal. But of course, that's just one case. but surely you'll get it right. It will work. Fingers crossed. Oh no. So, actually not. It didn't work, as usual. So, 2 years ago, a company from the Netherlands, a security company called Midnight Blue, published research that they called TETRA. And basically, this is 28 years after the algorithms were implemented in radios, so that's quite a long time. And actually, they said that they are not cryptographers, but they did some analysis of what they found. So, in case of TEA1, this encryption that you can use in a vegetable shop, but not really anywhere else, it has an 80-bit key, which is great, but there is a function which will just reduce the number of bits to 32, and only after that it will be used for encryption. So, and those 32 bits are easily brute forced. And in TEA3, the encryption is considered suspicious. These people say we are not cryptographers, and somebody else who is a real cryptographer should look into it. Also, there is no integrity protection in the protocol, so you can just basically flip random bits. There is a CRC, but you can also flip bits in it. So, and that makes active attacks possible, because you can retransmit stuff with bits flipped. For example, keystring recovery attacks. And notice that there is also TEA2 here, which was, they said that it looks okay. And that was the one that the police were supposed to use. But there is no TEA4, because actually they couldn't find it in any radio. And these are, if you look at the conference slides later, watch and read those presentations. It's really fun. Actually, when looking at tender documents in Poland, guess which encryption algorithm was written in the police tender documents? Any guess? Yeah, vegetable shot encryption, of course. Why use the one for police? Okay, so of course NC has some commentary to this. For example, saying that reducing the key length from 80 bits to 32 is not a deliberate backdoor. Might have happened by accident. Okay. So next year, SC decided that maybe it's a good idea to publish the algorithm specifications since they are out anyway, and that it included TEA4. And actually, there was the Midnight Blue guys did analysis of this TEA4 cipher, and it is weakened, but it is weakened according to the Wassenaar agreement specifications. So the key length effectively is around 56 bits, which is like the number of bits in a key that can be exportable. And also they published 3 new protocols, and this time with specifications, so that's pretty good. And another key exchange protocol. And it seems that the TEA7, for example, that it is also weakened, and probably with some speedups also, but that's something for cryptographers to play around with. This is the Okay, but if something is not secret enough, then use encryption, right? That will solve everything. And there is something called end-to-end encryption. It's not the end-to-end encryption that you think of, like the one that you have on your phones in Signal, but it's some other encryption. So it is expensive, as you would expect. It's not readily available, and since it keeps secrets, it has to be secret, right? And this time, we'll get it right. This time there will be no problems. Like, what would possibly go wrong? So, a month ago, Midnight Blue published yet another research dealing with end-to-end encryption and also dealing with stuff that they didn't find previously. So they reverse engineered it from radios. It turns out, for example, that there is a very popular algorithm 135, which is actually a yes-128 with the key links effectively reduced to 56 bits. And also it has no replay protection. So I said that TETRA is often used in industrial control. So basically you send a text message and it will, for example, disable power or enable power or turn on a pump or do whatever else. So an attacker can record this message and he can replay it and basically do the same. So for example, turn off power. And they also found some other problems. And one of the problems is that the keys actually seem to be the same for all algorithms. So if you are trying to merge from TA1, the vegetable shop encryption, to the TA2, which is the European police encryption, then at some point in time you will have two protocols running. So you can recover the key from the weaker protocol and use it for the stronger protocol. Oh, and by the way, our police force is migrating to TA2, I think, or they migrated, I think. At least looking at the tender documents, because this is the only source of data which we have. And also, they've said that there is a fix for the keystring recovery attack by SC, but actually it's not. They demonstrated it's not effective. And of course links, which I encourage you to watch and read. So, summary, can it be used for amateur radio? Of course. Is non-public encryption, does it work? Always. And one thing that, like looking at this from the perspective of a user, I'd rather have a protocol where I see the whole implementation, like M17, where the voice codec doesn't cost me, like in M17, right? Where I can verify how the cryptography works, right? Because it's possible to add whatever you want to this protocol. And I can also verify basically stuff in a radio, like message handling, whatever. See if there is not a buffer overflow, or I can, I don't know, re-implement something in Rust because that's like fashionable today. So